Hi everyone and welcome. In today's lesson, we are going to learn about indefinite integrals. To get started, let's begin with the definition of an antiderivative. A function capital F is said to be an antiderivative of a function lowercase f on some open interval ab if capital F differentiates into lowercase f. So previously in differential calculus, we were given a function and then we were trying to differentiate and get a new function. But now you're given a function and you want to go backwards. You want to figure out what is the function that differentiates into this given function. That is called an antiderivative. As a simple example, let's say we're given f of x equals x. Then if I ask you to differentiate this, you would just get f prime is equal to 1. But we are not looking for this. We are looking for a function that differentiates into this. And in this case, take capital F of x to be 1/2 x squared. Then capital F prime is going to be, by the power rule, you bring the 2 down, it cancels with this 1/2, and you just get x, which is exactly the given function. And so we say capital F is an antiderivative of lowercase f of x equals x. Please note that antiderivatives are not unique. I know that 1/2 x squared is an antiderivative, but so is 1/2 x squared plus 17, or 1/2 x squared minus square root of 2. In fact, it's going to be 1/2 x squared plus any constant. You can add any constant because when you go ahead and differentiate this, you can apply the sum rule for the derivatives, and the derivative of the constant is just going to be 0. And this piece will differentiate to x. And so these are all antiderivatives of the given function f of x equals x. To get a geometric understanding of what is going on with these plus c constants, let's graph the antiderivative 1/2 x squared. It's just a parabola that has a vertical compression, but it's going to look something like this. And when you add a constant like plus 3 or plus 0 or minus square root 2, it's just going to shift the graph up and down, as you can see here. Now, vertically shifting a graph will move the tangent lines, but it will do so without changing the slopes. For instance, consider the same point on each graph. The tangent line drawn at those points are going to be parallel. They're going to have the exact same slopes. As another example, take these 3 similar points on all 3 graphs. The tangent lines drawn at this point are all going to be parallel. They're just shifted copies of one another. And so when you differentiate each of these functions, the derivative will be the same because the slope everywhere is identical. The slope everywhere is identical. They all have parallel slopes. So when you differentiate any of these functions, their derivative is just going to be given by, in this case, f of x equals x. This function captures the slope of each of these functions. Moving the graph up and down doesn't affect the slope. And so what we see here is that when you find the antiderivative of a function, you get multiple answers because all of these shifted copies have parallel slopes. And so all of these functions can be represented by the same derivative in this case. Now, a question that you might have is, are there other types of antiderivatives of f of x equals x other than just shifted copies of the parabola of 1/2 x squared, right? Is there any other kinds of weird functions that differentiate into x? It turns out the answer is no. So there's a very important result here that says that if capital F of x is an antiderivative of lowercase f on some open interval, then every antiderivative on this given interval is just going to be this particular antiderivative plus some constant. In other words, if you have an antiderivative and I have an antiderivative for some given function lowercase f on some open interval, then both of our functions are going to be very, very similar. They're just going to differ by some constant. This process of finding antiderivatives, that is functions that differentiate to a given function, is called antidifferentiation or integration. And here is the notation that we will start using for antiderivatives. So let's say you're given a function lowercase f, and you ended up finding an antiderivative for it, capital F, right? So capital F differentiates into lowercase f, and hence it's an antiderivative. Then as we just discussed above, the most general antiderivative is going to be this particular antiderivative plus a constant, the shifted copies of this particular antiderivative. To represent this entire family of antiderivatives, we are going to use this integral sign. So the integral, and there's going to be no bounds here. Okay, so it's different from the definite integral where we had bounds. This has no bounds. It's just the integral of lowercase f of x dx. This notation is what we're going to use to represent the most general antiderivative of lowercase f. Okay, so capital F of x plus c is the most general antiderivative or the indefinite integral of lowercase f. And instead of using these symbols, you can use this integral sign, this indefinite integral of f of x dx. So now it's a good spot to compare definite versus indefinite integrals. You might have questions about, are they similar? Are they the same thing? What's the connection here? Well, it turns out that definite integrals and indefinite integrals are two very different objects. This is like comparing apples to like bricks, two completely different things. The definite integral is just a numerical number, and it's obtained as a limit of Riemann sums. Whereas the indefinite integral represents an entire family of functions, an infinite family of functions, whose derivative is some given function. And so these are two very, very different objects. One is just a number, and the other is a whole family of functions. So now you might be wondering, how can we use such similar notation to represent these two very different objects? Isn't that kind of confusing? Well, it turns out that there's a very nice relationship between these two very different objects, and it's going to be given by something called the fundamental theorem of calculus that we will take a look at in future lessons. Next, let's work on some antiderivative formulas, some integral formulas. The first thing that we're going to do is reverse the power rule for derivatives. So here is the power rule for integrals. Let's say you want to find the antiderivative of a power function. It turns out that the general rule is add 1 to the exponent and then divide by the new exponent, and then plus c to get the entire family of antiderivatives. To check any antiderivative formula, it's very simple. Just go ahead and differentiate the answer and you should get the integrand, and that will verify the result. So I encourage you, as we go through this video and I introduce new indefinite integral formulas, go ahead and verify them for yourself to see that they actually work. So let's verify this one. If I go ahead and differentiate this function, so d by dx of this function, the derivative of the first function, just using the power rule for derivatives, you bring the a plus 1 down, and it will cancel with the a plus 1 down here. And then you subtract 1 from the exponent, so you'll get x to the a. And then the derivative of a constant is just 0. So yes, this is indeed an antiderivative because it differentiates into the integrand. Now, another thing I would like to note here is that the power rule for derivatives worked for any real number exponent. But for the power rule for integrals, you have to be a little bit more careful. It does not work when the exponent is -1. Because if your exponent was -1, then you would add 1 to the exponent to get x to the 0. And then you would have to divide by the new exponent, which would be 0. And that would be an undefined expression. So as a result, you cannot apply the power rule when the exponent is -1. But if it's not -1, then you can go ahead and apply this rule. It doesn't matter if you have a fractional exponent or decimal exponent or integer exponent, you're free to use it. And so let me show you the power of this power rule. So definitely it's going to let you find the antiderivative of simple polynomial functions like this. So the antiderivative of x dx is just going to be add 1 to the exponent, so you get 2, divide by the new exponent, plus c. And this also verifies the example at the beginning of the lecture. We found the antiderivative of x before, and we claimed it was this. And so this rule also agrees with that. We can also use the power rule for integrals to find the antiderivative of something looking like this. Now, this does not look like a power function. It's not x raised to the power of something. But if you remember your exponent rules, you can rewrite this with a negative exponent, x to the -9. And now the power rule does apply. You add 1 to the exponent, you get -8. Then you divide by the new exponent, like this. And then you add a constant to represent the most general antiderivative. And lastly, the power rule for integrals will also help you find the antiderivative of these radical functions. So this does not look like a power function. However, if you remember your exponent properties, this radical symbol just means the 1 over nth power, a fractional power. As a result, we can just rewrite the fifth root of x cubed as x raised to the 3 over 5 power. Now it is in this form. It's a power function. So the power rule for integral says add 1 to the exponent. If you add 1 to 3/5, you get 8/5. And now you have to divide by this new fraction. And please be careful. Don't put 8 over 5 like that. That's incorrect. You have to divide by this new fraction, 8 over 5. And dividing by a fraction means multiplying by the flip. So you would actually get 5 over 8 as the coefficient over here, times x to the 8 over 5, plus c to represent the most general antiderivative. Right? These indefinite integrals, they represent not a particular antiderivative, but the entire family. The most general antiderivative is represented by the indefinite integral. Next, let's quickly cover what happens when the exponent happens to be -1. That is, we're trying to find an antiderivative of x to the -1. Well, from your differential calculus course, you probably learned that the derivative of the natural logarithm is 1 over x. So that means an antiderivative of 1 over x is ln x because it differentiates into 1 over x. However, there's a small issue with this. The reciprocal function is defined for all non-zero x, whereas the claimed antiderivative is only defined for positive inputs. So we would like to have an antiderivative that agrees with the entire domain. So maybe in your differential calculus course, it was also mentioned that the derivative of the natural log of absolute value of x is also 1 over x. And the great thing about this function is that it's defined for all non-zero x. It's a clever way of extending the domain of the natural logarithm. And it also keeps the derivative unchanged as 1 over x. So this means that an antiderivative of 1 over x over its entire domain is going to be natural log of absolute value of x plus c to represent the most general antiderivative. Now there are some technicalities here, like there's two separate domains here that lead to two different constants of integration. So we could make a separate video going through the derivation of this formula and those technicalities. But for this video, the thing I want you to really remember here is that the antiderivative of 1 over x dx is not natural log of x, but natural log of absolute value of x plus c. Next, let's take a look at some more properties of the indefinite integral. This is the linearity property of the indefinite integral. It says that if you want to find the antiderivative of a sum of two functions, then you can just find the antiderivative of each piece and add them together. And this is like the constant multiple rule. If you're trying to find the antiderivative of a scaled up version of a function, well, then you can find the antiderivative of f of x and you scale that antiderivative by c. And you might be saying, isn't this obvious? This is just like the definite integral properties. But keep in mind that those are two very different objects. So it's actually not obvious why these properties follow. And to prove these properties, they will actually come from properties of derivatives, not from sums, which is where the properties of the definite integral come from. So for our purposes, we just have to know how to apply these rules, and it's actually very intuitive. Let's say we want to find the antiderivative of this function over here. As you can see, it's a sum and difference of a few different components, and there's also like scalar multiples at the beginning. So the idea is that these linearity properties allows us to take this integral sign and distribute it to each sum and difference, and then also like pull out these constants from each term. Basically, you can push this integral sign as deep as possible within each term. And the resulting expression that we get is this one. So for instance, if you take a look at the second term, the integral sign got applied here, and then the minus 5 also got factored out. So we got minus 5, the antiderivative of x raised to the 2/3 dx. And so now we can just go ahead and find the antiderivative of each piece and add up the results. So for the first antiderivative, we just use the power rule. We add 1 to the exponent, it becomes fifth power, divided by the new exponent. You leave the constant at the beginning just there. Similarly, for the next antiderivative, we have to use power rule. We add 1 to the exponent 2/3 to get 5/3, and then you have to divide by 5/3. For the next antiderivative, we add 1 to the exponent, we get -2, x to the -2, then you have to divide by the new exponent, so divide by -2. And lastly, we're trying to find the antiderivative of x to the -1. For this, we just discussed the special rule that it's going to be ln of absolute value of x. Now, a question you might have is, do we need a constant of integration for each of these antiderivatives that we took? Well, technically yes, but you can just take all of those constants and combine it into one new constant and call it c. Now we just simplify. You can bring like the constants at the beginning, so 3/5 x to the power of 5. And over here, you see that we are dividing by 5/3. So that's the same thing as multiplying by 3 over 5. And so the 5's cancel, and you just get a coefficient of -3 at the beginning, and then multiplied by x to the 5/3. Over here, we just have -1/2 x to the -2. And then this is just negative square root 2 natural log of absolute value of x plus c. And that is our most general antiderivative of this function. This is a good tip when you're first doing these problems. You can always check your work. Even on tests and exams, I recommend that if you have extra time, go ahead and differentiate the answer and make sure that it equals the integrand. Next, I will actually discuss a few more integral formulas, and these are just going to follow from the differentiation formulas that you already know from differential calculus. The first formula says that the most general antiderivative of 0 is a constant. That should make sense because when you differentiate a constant, any constant differentiates to just 0. Another way to remember this rule is you can think of this as a special case of the power rule. Just think of this as x to the 0. Then the power rule says that you have to add 1 to the exponent, divide by the new exponent, and there's still a coefficient of 0 here, plus c. So 0 times all of this is just going to be 0, and the result is just going to be c. So you can remember it like that, or just remember that the derivative of any constant gives you 0, hence a constant is the antiderivative of 0. The next integral formula says that the most general antiderivative of a constant function, f of x equals k, is going to be a linear function, kx plus c. This should make sense because the derivative of a linear function is going to be the slope, right? It's just going to be the constant. Another way to think about this formula is a special case of the power rule. Just think of this as kx to the 0 power. And then the power rule says that you have to add 1 to the exponent divided by the new exponent and plus c. And so you get kx plus c. Next up, we have a few trigonometric antiderivative formulas. And these just come straight from the differentiation formulas. For example, I know that the derivative of sine is cosine. As a result, the antiderivative of cosine is going to be sine x plus c. Similarly, if you were to differentiate minus cosine x, you would get minus sine x, and then the minus cancel, and you just get sine x, right? Which is the integrand. And so that's how you can verify these formulas. The antiderivative of sine x dx is going to be minus cosine x plus c. Similarly, the most general antiderivative of secant squared is going to be tangent x plus c, because tangent differentiates into secant squared. And you can check the same formulas for the last three over here. You can pause and write them down or reason about why they're antiderivatives. It's because the right-hand side differentiates into the integrand. And so these are all going to be antiderivatives of the integrand. Next up, we know that the exponential base e is a very special function. The derivative of e to the x is itself e to the x. So if I asked you, what is a function that differentiates into e to the x? Well, it would just be e to the x, right? E to the x differentiates into e to the x. As a result, e to the x is its own antiderivative. The most general antiderivative of e to the x is e to the x plus c. And here's a slightly more interesting rule. If we're trying to find the most general antiderivative of e to the kx, well, then you're going to get e to the kx, but you have to divide by this number, this constant number k. And over here, I'm assuming k is a non-zero constant, otherwise it won't work. We can also verify this formula very quickly. If we differentiate the right-hand side, well, I know I can leave the constant there. The derivative of e to the kx is e to the kx, right? The derivative of e to anything is e to anything. But then you have to multiply by the derivative of the inside function, which is k. These k's cancel, and you're left with the integrand. So indeed, it is an antiderivative, and this is the most general antiderivative of e to the kx. Now let's take a look at a few examples involving these new formulas that we just discussed. For our first example, we are trying to find the most general antiderivative of sine t plus 20 secant squared t. So using the linearity property, we can just find the antiderivative of each component. The antiderivative of sine is negative cosine. The antiderivative of secant squared is tangent. And so the final answer is just going to be a negative cosine t plus the 20 tangent t plus the constant of integration. For the next example, we have the indefinite integral of secant theta times, in brackets, secant theta plus tangent theta. Now, if you notice, I haven't mentioned anything about products or quotients. So in order to solve this problem, we will have to somehow algebraically manipulate the integrand so that it becomes a sum or difference of functions. So in this case, I'm going to distribute the secant to each term in the bracket to get secant squared theta plus secant theta tangent theta. And now I'll just find the antiderivative of each piece. The antiderivative of secant squared is tangent. And then the antiderivative of secant theta tangent theta is secant theta, right? Secant theta is what differentiates into secant tan. And then finally, plus the constant of integration. You can't forget that, because the indefinite integral represents an entire family of functions. It's the most general antiderivative, not just a particular one. And lastly, here are some examples involving the exponential rules. So if I want to find the antiderivative of 3e to the x minus 4, we can just go ahead and find the antiderivative of each piece. So we push the integral sign through, we pull the constants out, and yeah, the antiderivative of e to the x is e to the x. Very nice. And then what's the antiderivative of a constant? Well, you can think of it as x to the 0 and then apply the power rule, and you will add 1 to the exponent divided by the new exponent. In other words, you just pick up x. It becomes a linear term. And then plus the constant of integration. And here's the last example. We want to find the most general antiderivative of 12 times e all raised to the 7 minus 3x. Now we do have a rule for finding the antiderivative if we have e raised to the kx, where k is a non-zero constant. But it didn't say anything about adding a new constant like d. So as a result, we will have to manipulate this form a little bit. To do so, we have to remember our exponent rules. We can actually split this into two different exponents. So we can write this as e to the 7 times e to the minus 3. Because if you have the same base being multiplied, you add the exponents and you get exactly this exponential. Next, 12 times e to the 7 is just a constant. It's just a number. You can just bring it out of the integral sign. And so we have to find the antiderivative of e to the minus 3x. Now we can go ahead and apply that rule that we discussed. The antiderivative is just going to be e to the minus 3x divided by that k, so times 1 over minus 3. Now we can clean this up because 12 divided by minus 3 is minus 4. And then you can take these exponentials and make it into one big exponential by adding their exponents. And you will get back to e to the 7 minus 3x plus the constant of integration. And that brings us to the end of today's video, in which we learned about antiderivatives and indefinite integrals. It turns out that the indefinite integral represents the most general antiderivative. In the next video, we're going to take a look at an application of indefinite integrals and antiderivatives as it relates to simple differential equations and initial value problems. And then after that, we're going to move on to the fundamental theorem of calculus and see how the definite integral and the indefinite integral are related, even though they're two completely different objects. And so I hope you're excited to learn about those ideas, and I hope to see you in those future lessons. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.